We shall now discuss on a topic that is not very much related to the electrical engineering aspects that we have been discussing till now. However, this is nonetheless a very important topic, especially if you want to compare, benchmark, reference the many systems that we have been discussing. You see, in photovoltaics, renewable energy systems, take for example the PV modules, PV panels, they have a lifetime of around 20-25 years. Take for example batteries, they may last for around 5 years. So which means that you may have to replace the battery sets in between. Take the electronics. Electronics may also have a very large lifespan. So a photovoltaic system contains many subsystems, and these subsystems have different lifespans. So when you have comparable systems, how do you benchmark them? How do you compare them? What is the value of the particular system? What is the value for the money and what is the value for the system? What are the economics for the various system, and how do they play, how do the variables play, and how do you obtain the unit costs. Unit costs meaning that if it is a water pumping system, what is the cost of a unit of water? If it is an electricity generation system like the PV connected to the grid, what is the cost of 1 unit of electricity? So how do you arrive at that? So for that you have to consider the lifetime of all the subcomponents, the replacements, maintenance, all these issues will start coming into picture. So it is that point that we would like to address. It is from an engineering perspective that we will look at it. It is not exactly to arrive at the exact cost, more from a draft economic analysis, so that we will be able to compare many systems. And that is what we would aim to do in this topic of life cycle costing. Consider an item. Now this item has a value, and this value is related to time. So it has a value at a given time instant, or we could say at a time frame of reference. It could be now, it could be tomorrow, it could be 10 years from now, but the value of the item is coupled, directly coupled with time. Now this item is either bought or sold. So there is a transaction where you will buy this item or sell this item, and the medium through which you will buy or sell would be by using this money as an item, money as the medium. So the money is also having a value, and that value again is time dependent. Now with time, the value of the money can grow. So there is growth in the value of the money with time. Of course, the growth can be positive or negative, but most of the time it is positive. As time progresses, the value of the money increases, and that is what we tell interest. So there is an interest rate which can be used for calculating by how much the value of the money has grown. Likewise, an item also with time, its value can increase or decrease. There is growth or change in the value of the item, and it is called inflation. So let us look at this growth profile of this item and the money, and try to bring in that relationship and use that relationship to measure the life cycle cost. The interest and inflation have various growth profiles. So one can model it with different growth profiles. One simple way is the linear growth. Another way is called the compound growth. A third way, exponential growth. The compound growth, very popular, is also called the discrete compound growth, and the exponential growth is called continuous compound growth. We will see how these relationships come about. First, consider the linear growth. Simple interest is a typical example of linear growth. There the key variable is I, which is called the rate of interest. N is the number of intervals. Now the rate of interest is for an interval of time delta t, and n is a variable associated with the number of time intervals delta t under consideration. So if you say delta t, the time interval is 1 year, which is what most commonly is used in banking, number of years under consideration, n will be number of years. You can visualize this with the timeline. Let me draw the timeline versus t, x-axis, and I will put several equi-spaced tick marks like this to represent the intervals. So this interval is delta t, and I will call this one as interval 1, interval 2, interval 3, interval 4, and so on. This is interval n. This is the nth interval. Now there is another variable I will introduce. It is the called variable s. Now let us say at this point, at the beginning of this interval or the ending of the previous interval, I will mark it as s0, s0. At the end of the first interval, I will call it as s1. At the end of the second interval, it's called s2. At the end of the third interval, s3, s4, so on. At the end of the nth interval, it will be sn. Now what is the meaning of sn? Sn is sum after nth interval, sum after n intervals of time that has elapsed. So if S0 was the sum at the end of the 0th interval, this is the sum that you have at the start, beginning. After n intervals have elapsed, the sum at the end is Sn. So that is called sum after nth interval. If each interval is 1 year, then it would mean sum after n years. Now S1 is given by the relationship, linear relationship S0 plus S0 into I, where I is the rate of interest for the interval. So if delta t is the interval and then this is just one interval, S0 plus S0 into I, which is S0 into 1 plus I. Now S2 is S0 plus S0 into 2 intervals have elapsed, so 2 into I. So that is S0 into 1 plus 2I. And if I move it up, so on, Sn would be S0 plus S0 into Ni, which will be S0 into 1 plus Ni. So this is the relationship that you would get for the sum after n intervals or time periods have elapsed with the rate of interest I and with the starting value of S0. This is termed as the simple interest equation. Let us now discuss compound growth. An example of this, of course, is the compound interest. You may be aware of the compound interest formula. Here too, like simple interest, there is a variable I which represents the rate of interest for delta t interval of time. N is the number of intervals, delta t intervals, that are being considered. Now let us visualize again like before on a timeline, and I will mark equi-spaced tick marks like this, and each interval here is what I will call delta t time interval. So that is delta t. Now that will be interval 1, this is interval 1, this is interval 2, interval 3, interval 4. Now this is interval n. So this will be n plus 1. So let me take this at this point. You have S naught, the sum, that is the starting sum at the end of the 0th interval or at the beginning of the first interval. Now at the end of the first interval I have sum S1, at the end of second interval sum S2, at the end of third interval sum S3, sum S4, and at the end of nth interval it is sum Sn. At this point it will be sum S minus 1, and here it will be sum S plus 1. So now let us try to find out what is S1. Now S1 is equal to S naught plus S naught into I. This is same like in simple interest case or in the linear growth case. And this is equal to S naught into 1 plus I. Now S2 is S1 plus S1 into I, one step application. So for S2, S1 is the previous sum. So if you do one step application, S1 plus S1 into I, which is S1 into 1 plus I, and S1 actually we know is S naught into 1 plus I, and therefore substituting you will have S naught into 1 plus I into 1 plus I, so it is S naught into 1 plus I whole square. So in the same way Sn will be S naught into 1 plus I whole to the power of n. So this formula, this equation is the compound interest equation. So if S naught is the starting value you start, and I is the rate of interest for each interval, n is the number of intervals. So if delta t is 1 year, n will be the number of years. So if you began with S naught, at the end of nth year, the sum would have grown to S naught to 1 plus I to the power of n. Now let us consider the exponential growth model. So in the exponential growth model, basically we would expand the compound interest model in this fashion. Here let I be the rate of interest for 1 year, and m be the number of intervals 1 year is divided into. So note the slight difference in definition. I is the rate of interest for 1 year, whole year, and m is the number of intervals that 1 year would be divided into. Then delta t is nothing but 1 year by m. 1 by m is delta t, and the interest in an interval would be I by m. So interest per interval. The rate of interest per interval will be I by m. So this is the rate of interest per interval. Now let me draw the timeline as before. Now I am going to mark off equispaced ticks on the timeline. Now each of these spaces will represent a year. So this is year 1, this is year 2, so on. This is year n. And each year is divided into m intervals, smaller intervals like this, so on. And the time period between this interval is delta t, which is 1 by m. Now I can say this is sub interval 1, 2, 3, 4, so on up to m. And the second year is also divided up to m intervals. Nth year is also divided into m intervals, each of width delta t. Now at the beginning of year 1 we will have S0. At the end of year 1 we have S1. At the end of year 2 S2. And at the end of year n it is Sn. We are of course interested in finding what is Sn. Now let us apply the compound interest model. Sn equals S0, the starting, 1 plus I was the original compound interest model. Here the interest per interval is I by m. So 1 plus I by m. And how many intervals are there? There are n years, and each year has m intervals, so n into m intervals. So this would be the discrete compounding formula. Now let us reassign I by m to x, some another variable x is equal to I by m. Then what is m? M is equal to I by x. Now substituting, you have Sn is equal to S0, 1 plus x, I into n by x. So now in this, as m tends to infinity, x will tend to 0. X tends to 0. So let us apply the limit as x tends to 0 for this equation. The limit of x tends to 0, Sn will be limit as x tends to 0, S0 into 1 plus x to the power of 1 by x whole to the power of I into n. So this is actually split into 1 by x and I into n. So that is how this has come about. So this can be written as S0 into limit as x tends to 0. This limit is 1 plus x to the power of 1 by x whole to the power of I into n. Now this limit as x tends to 0, 1 plus x to the power of 1 by x is the definition of E. So this is defined as E. Therefore I can write it as S0 into e to the power of I n. Sn is equal to S0 e to the power of I n is the exponential growth model. It is also called continuous compounding because you don't have discrete intervals, because m, the number of intervals, has tended to infinity. It's called continuous compounding.